Hi, this is my overview of my final project, the technical breakdown of the OBD2 PowerPal, which is now a embedded digital real-time display that communicates with my car's onboard computer and displays on an OLED display. In part 1, I showed the device operating in the car. Now I'll walk through the hardware design, communication architecture, wiring, and how the system interfaces with the vehicle's CAN bus. So this was the video I already showed. I'll also include this presentation so you guys can watch it later.
Hello.
Ooh. This project is a real-time automotive telemetry device built around an ESP32, an MCP2515 CAN controller with a TJA 1050 transceiver, and a 1-inch 128x64 OLED. Even though this isn't a mobile robot, it still uses all the key skills from COM444: microcontroller programming, sensor communication, timing, control loops, and hardware debugging. The main goal is to read live engine data from my car's ECU and render it in a safe, readable dashboard format. Hardware architecture. This slide shows all the major hardware components. The ESP32 acts as the main processor, which is a lot similar to Arduino Uno or Arduino Mini. The MCP handles CAN bus protocol. The TJA converts logic level CAN signals to automotive differential CAN. The OLED displays the parsed values. The buck converter is a step-down transformer, which safely regulates the 12 volts from my car down to 5 volts for the ESP32. The MCP uses an 8 MHz crystal oscillator, which ensures accurate CAN timing and maintains proper bit rates on the CAN network. I kind of like this. I found this trippy that it used a crystal wiggling to convert. I like that quite a bit. Wiring overview. This slide shows the wiring flow through the system. OBD2 pins 6 and 14 carry CAN high and CAN low into the TJA. The TJA interfaces with the MCP via differential signaling. The MCP communicates over SPI with the ESP32. The OLED communicates over I2C with the ESP32. Power enters from OBD pin 16 at 12 volts, is stepped down through the buck converter, then powers the ESP32 and display. The wiring mirrors the structure of embedded systems used in robotics. Sensors in, microcontroller processing, output to an actuator or display. So display in this case. ESP32 pin mapping. This slide lists the exact ESP32 pins connected to each component. For the CAN module, CS goes into GPIO5, INT goes into GPIO4, MISO to GP19, MOSI to GP23, SCK to GP18. For the OLED, SDA to 21, SCL to 22. These match the hardware wiring in my actual device, and they map directly to the SPI and I2C peripherals. This is an example of the pinout on the ESP32. This is the ESP32 on my actual board. So I picked this up from Lee's Electronics, which is a local hardware shop in Vancouver. I liked going there. It was a really cool shop. It had a lot of cool things, just kind of going through the aisles and discovering things like cool LEDs and getting some inspiration for new projects. On the negative side, it was hard for me to find specific parts, so I ended up getting most of my parts from Amazon. So yeah, this actually shows it. Another challenge I had with this project was sometimes I'd pick up parts and I couldn't find the documentation for the parts. So this ESP32 was one of those. I immediately plugged it into the breadboard, but I didn't realize if I flipped it over, it had the silk screen of the pinouts on it. But if I was to do this project again, I would get an ESP32 with the pinouts written on the top so that I could see where to pin. I had to do a lot of mental math going back to this, and then corresponding it to the breadboard, which is all right because row 1 is at 1. But yeah, it caused a lot of mental gymnastics there for sure. And yeah, this project uses 3 different voltages actually. The input from the OBD, 12 volts, steps down to 5. That feeds into the main 5.5 volt in. The MCP also uses 5 volts, so that goes on the 5 volt side. And then on the 3 volt side, the OLED uses the 3.3 volt. So there's 3 different voltages going on in the project, and it was very important to tie all of the grounds into a common rail, so then all the grounds go back to a common rail in the project. This is an example of the OBD2 standard. So I was kind of surprised that it has 16 available pins, but for the project I only needed like 4 or 5 of them. So most of the wires end up unused. I picked up from Amazon an OBD2 to tails thing, or OBD2 to tails component. I stripped some of these and soldered them into the buck converter, and then the can high and can low screw in through set screws into the can shield. So yeah, there's can high, can low, there was a 12 volt, and then there was 2 grounds. There was chassis ground and signal ground. CAN bus communication flow. This is the full communication chain. The ESP32 sends an OBD2 request using SPI to the MCP. The MCP formats the request into a CAN frame. The TJA transmits the frame as a differential CAN to the car. The vehicle's ECU responds with the CAN frame. The TJA and MCP receive the frame. The ESP32 reads the raw bytes over SPI and parses the response. This follows multi-layer communication model used in robotics communication systems. Oh yeah, and here's from the Amazon page, my MCP 2515 chip, which is kind of funny because I'm looking at it right now on my desk and it doesn't exactly correspond to that. So it was another example of when these parts arrive, they're not always exactly as pictured or as documented. So I have to do a little tweaking, and even when I bought from Lee's Electronics, the ESP32 didn't come with much documentation either. So that was something I found interesting and kind of funny. But you can see here the CAN bus interface on this side. It has the set screws, so I just stripped the wires and put them in the set screws. And then I used DuPont connectors to connect to these to communicate. And then on this side, it goes out to the ESP32. CAN frame extraction. Each OBD2 PID returns specific bytes. For example, speed. It is 1 byte, direct kilometers per hour. And I think in the future I might want to add a button to convert it to miles per hour as well. I'll have to add a additional button, or I might want to change to like an touchscreen OLED display. I'm going to figure that out in the future, kind of figuring out how I want to do an enclosure on the system as well at the end. So far, I have been using it every day for 2 weeks. It's been quite a useful device, and I like it. I even showed it to a guy from my work. He has a 2007 Ford Ranger, and he wants me to build one for him too. So I felt that was kind of fun. So for the RPM, it's 2 bytes, and then I use a formula to convert it. A times 256 plus B, all divided by 4. Voltage. It's manufacturer dependent, so in this case Ford, interpreted as millivolts in this design. The ESP32 converts these bytes into human readable values before sending them to the display. So early on in testing I should have taken a picture, but in the serial monitor it had all the frames coming from the car and it was crazy. It was just like all these hexadecimal values constantly scrolling from the car's computer. OLED rendering. So yeah, it uses I2C communication. It uses the U8G2 driver, font selection, and real-time updates. So you can see it here. Yeah, speed, which would be a maximum of 3 digits. So I shared that with the battery, which is also 3 digits. The main inspiration for my project was the parasitic drain in my older vehicle. So I find when I start the car in accessory mode, I can see the resting voltage before the power goes onto the car. So it's helped me monitor the voltage, and I can see how it drops over time. And RPM, because it's 4 digits, I wanted it to be on the bottom and centered. And then also I have the code going so that it draws the largest values it can, and they're about as big as the values on the car. It's been really useful for me driving and sticking to speeds, because you can see on the actual display I only have 20, 40, 60, 80. So I'd like 50, it's hard to kind of see 50, it's hard to see 30 for school zones. And some of the others too, like 70 and 90 as well, are hard to see. It's quite a small instrument cluster as well. And I found the RPM interesting too. It's quite fine-tuned, and it is a manual transmission, so that's been cool to see. I wanted to do a note on safety considerations. So my design is a bit different than what I originally intended on. My original design was going to detect if the voltage was low, disconnect the battery, and then through the ESP32's onboard wireless, like send me a message somehow that my car battery had drained. But I had to consider kind of safety considerations, like, is that safe for a robot in this application to disconnect a car battery? Like when I start my car, the voltage drops down initially in order to turn the crank and get the car started. So I kind of had to consider the ethics of if the robot is safe to use in that situation. For safety, the system is designed to be entirely read-only. It never sends any write commands or controls any actuators. I intentionally avoided features like battery disconnect relays or load controllers because interfering with the vehicle's electrical system while driving can be dangerous. This approach ensures the device is safe and non-disruptive. Skills demonstrated. This project integrated multiple skills from the course Comp 444. Embedded C++ programming, SPI and I2C communication for the OLED display, real-time control loops, microcontroller hardware wiring, parsing structured sensor data, debugging timing and communication errors, and designing an embedded UI layout. I also got to practice some other skills, like I picked up a voltage meter, like when I had to adjust the buck converter, it uses a set screw, so it could be up to 60 volts. And so I plugged my meter in, and then turned this set screw down until it was the 5 volts input for the ESP32. I also got to practice soldering as well. I soldered the connections into the buck converter from the OBD2, and I mostly used DuPont connectors or reused the connectors from our robotics kit. And then for the OLED display, it didn't come with any DuPont connectors, so I had to do very fine soldering down into the display. So right now it's kind of on a 12-inch cable. In the future, I'd like to maybe take like a USB cable and strip it down, and then put the OLED into a little enclosure as well. So then I can also put the rest of the device into an enclosure and hide it under my dashboard somewhere safe, and then have a little display up where I could move it around. Code walkthrough video, so I'll include it in this slideshow, but I'll also embed it in my post for this final project for review. And I'll also include a GitHub link to the code as well. Oops.
Well,
In conclusion, this concludes the technical breakdown of the project. And yeah, I guess I'll just share. I think I shared some of the lessons I learned. Like I'm definitely quite inspired by this course. I didn't think I would be when I was just doing the labs, like kind of following instructions. But when I applied these concepts to solving a real problem, I made something quite useful that I've been using every day for the last 2 weeks. Nothing's going to waste, and I'm inspired to make some other projects too. I'd like to. I've seen some artists online have made animatronic Furbies and a big mouth Billy Bass, and they've hacked it with Arduino so that it can pull in like a AI assistant, or the big mouth Billy Bass or Furbies can move their mouth to music and stuff. I'd like to create some interactive art and some stuff with OLEDs and music timing as well. So yeah, I'm definitely inspired, and I learned tons of new skills. I'd like to also try home automation things like custom built smart assistants for the home, uh, like that can draw blinds and do some like monitor temperature and do some other things as well. Like I definitely feel inspired, and like going to cool stores like Lee's Electronics, seeing kind of what's available in this maker hobbyist space. This is definitely one of the cooler courses I've done in my degree. I'm doing computer science, so most of my stuff has been software. So I can't really show it to people, but it's really cool to be able to show people what I built, uh, kind of taking these technical skills into the real world. And yeah, like people have definitely been impressed. Like my coworker who wants me to make some gauges for his Ford Ranger now, which I'll definitely do for sure. Yeah, this has been a great course, and I appreciate the time. And yeah, thanks a lot.